Okay, so I'm here today to talk to you guys a little bit about what we're doing, about how I think it can be applied to this kind of era of big science and the LSST, and to kind of talk a little bit about how there's a capacity out there which isn't CPU cycles on a machine, but actually thought cycles in somebody's head. And if we can tap into that, I think that there's value to be derived from that. It's not going to solve all the problems that we have. It's not going to even solve most of them, but there's a subset of problems and a subset of issues that it can be really useful to loop in human intelligence and human power to. So I want to talk a little bit about that. So we're based out of the Adler Planetarium. We're called the Zooniverse. It's not a wonderful name, but we're stuck with it now, unfortunately. And really, we started off our project by building this website, Galaxy Zoo. And this happened about 5 or 6 years ago now. And Galaxy Zoo was an experiment to see if we could take a large-scale astronomical data set, put it online, and have people tell us something interesting about it. And the problem that we initially looked at was galaxy morphology. So what is a spiral galaxy and elliptical galaxy? We built a very simple interface for it. We put it up. There was 4 buttons that users were asked to press to tell us something about the image they saw, and then they would see another image. And they would just go through it time and time and time again. And so we're basically crowdsourcing the scientific discovery, the scientific data analysis for a problem here, which wasn't at the time very well solved by machine learning algorithms. And it's tapping into the concept which has become a bit more broad, and we're hearing about it a little bit here. The creation of the internet, and especially Web 2.0, has basically changed the internet from being a place where people go to consume data and consume knowledge, and it's become a place where actually people are creating and they're innovating and they're providing value through the web and through Web 2.0. And this was very nicely summarized by this guy, Clay Shirky, in a book which is called Cognitive Surplus, Creativity and Generosity in a Connected Age. And Clay's idea is that actually there's a lot of capacity out there in people's attention and people's ability to create, ability to analyze, and ability to think, that if we can tap into, we can do things that benefit the world and benefit science and research. To give you an idea of what cognitive surplus looks like, there's kind of a spectrum of cognitive surplus. On one side, you've got making lolcats pictures, like I'm in your drawers eating your undies, which is actually it is one level of doing something creative and something actually creative online. At the other end, you've got things that we associate more with value, which is things like producing Wikipedia. Wikipedia is a huge collaboration of people in their spare time providing value to something. Recently, there's been a whole range of projects like Folda, eBird, Starburst at Home, which are trying to tap into that to do different interesting things with people online. To give you an idea of how much cognitive surplus there is out there, I found this really fun infographic about Angry Birds. If you've ever played Angry Birds, you'll know it's a very fun, addicting game. But just to give you an idea of how much time people have and how much time they're using on digital devices, every day about 200 million minutes of Angry Birds is played. That equates into about 380 years, which means that 1 hour, every hour, 16 years worth of Angry Birds is being played. I'm not sure if this is true anymore. This was a couple of months ago that I found this infographic, so it might have gone down a bit. But think about that. Every hour, 16 years worth of human attention is being focused on throwing Angry Birds across a screen. If that doesn't weird you out, you need to readjust your levels of what's acceptable in the world. I love this statistic as well. Players have hurled more than 100 billion Angry Birds. There are an estimated 100 billion real birds alive on planet Earth. So there's been more fake birds thrown in Angry Birds than there are real birds on the Earth. So if you can tap into even a tiny fraction of this attention and a tiny fraction of this cognitive surplus, and you can use it for something good, then that's an amazing resource to be able to have. And what I want to convince you of today is that there's multiple ways of doing that. They can provide real value, and it's not just limited to trivial tasks. So we built Galaxy Zoo originally. We've actually grown a lot since then. In the past 5 years, we've actually expanded to have 26-ish projects. We've expanded our subject areas to not just space-based projects, but projects about nature, climatology, history, the humanities even, and medical research. We partnered last year with Cancer Research UK to crowdsource analysis of medical data to try and help accelerate the search for cures for cancer, which is a pretty major partner and a pretty major project to be involved in. We have a community of about 8,500,000 citizen scientists. That's people who have come to one of our projects and contributed something to the endeavor. That translates into about 54 million classifications, which is what we call an interaction with a piece of data and the information that come back. The actual individual chunks of information that people have provided us actually, we think, is probably more like 500 billion pieces of individual information that people have contributed to data that we've shown them online. Along with that, we've had about 1,300,000 comments on our systems. We've published 55 scientific papers across most of our projects, and we've discovered 5-ish planets, which is pretty amazing. So people interacting with our projects, sitting at home using a web browser, have discovered planetary systems, which is pretty cool. And one of those systems is the first case of having 2 binary pairs of stars which are orbiting each other and having one planet going around one of those pairs of binary stars. And so a very unique, rare system. So they're doing interesting things, and I want to talk a little bit about how they're doing that and how we can push that forward into a new era. The key kind of element to their projects and what we do best is we produce simplified ways of interacting with the data. So we talk a lot about open data in the sciences, about putting data online and allowing people to find it and use it. But actually, for most people, that's not enough. You need to make the data accessible. And so what we do is actually we spend a lot of time crafting very intuitive, very easy to use interfaces like these. And I encourage you all to go online, even during the talk right now if you want to, and check out some of the interfaces that we've built. But they kind of fall into a number of different categories. One is using tools to mark out features in an image. So this is a project we're doing looking at these fans on Mars, looking at the directional components of those, which tell us about wind speeds on Mars. The Galaxy Zoo project is basically a decision tree model, so you're showing somebody an image and asking them to make choices about that image. We have transcription-based models where we're asking people to transcribe text on these old World War I logbooks, which tells us about the temperature and climate back then, which helps with climate science. And projects like Snapshot Serengeti, which if you try it, you will lose about 2 months of your life to. It's really addictive and really fun. Where we're asking people to identify animals in the Serengeti. So this is kind of a classification project again. And so the key thing of what we do is build these really intuitive interfaces that allow people to contribute with very little overhead in terms of understanding the tools or understanding the technology and just give us the information that we need. When we ask people why they do this as well, and I think this is an important thing to understand, the motivation behind the participation in these projects, our community of 800,000 people, when we ask them why they contribute to our projects, they tell us overwhelmingly, amongst all these different reasons, that they want to contribute to research. This is a community motivated not by fun, not by seeing pretty images, not by wanting to get involved in a larger community. They genuinely want to make a positive contribution to research. They're motivated by the fact that they want to contribute to science. A number of these people are people who went to school, got interested in science, but could never take it further as a career because of circumstances in their life and circumstances in their family. And this is a way that they can feel like they're being part of something, and that's interesting and important. And I kind of want you guys to bear that in mind as we go ahead. So I wanted to talk about 2 ways in which we produce science from this model and produce data from this model, and talk about how we can evolve those for the kind of the LSST era and this big data era. The first is kind of like our bread and butter. It's data classification and categorization. So we actually have a very simple system. The Zooniverse has always been kind of the simplest thing that works. And so really what happens is we've got a big store of data. We've got a server or a number of servers here which basically do one thing, and that's a user can say, give me something useful to do. And by useful to do, we mean show me a piece of data that I haven't seen before and hasn't been classified enough to be considered done. They use one of our interfaces to talk about it, and this is actually the interface that Phil Marshall here works on, Space Warp's interface. And then that interface produces some information which gets sent back and stored. And that's pretty much all our system does. It's fairly dumb. Up to date, most of the science we then produce from that database of what users have told us happens kind of after the fact. It happens by taking that database and processing it after we've collected all that information. And I'll talk a little bit about that in a second. So it really is like the simplest thing that works, and that's important for us because we're a relatively small team of people. We can't maintain large, complicated computing structures, and so this thing was like, to let us grow to the stage we are now, really important. So then, at the end of the day, you've got millions and millions and millions of statements about an object, and we show each kind of data chunk to multiple users, and so we get like overlapping opinions on that piece of data. And so the question then becomes, how do you take those opinions of that data and boil it down into something that you can use in science, boil it down to a result? The simplest thing to do would just be to take everybody who saw a given galaxy image or a given plot of Mars, take their answers and do a sort of consensus vote on them. Just say like, this is the sort of the most common answer, and so therefore that's the answer for that piece of data. It turns out that works kind of okay, but you can do better, and that's kind of a big part of what we do, and is trying to get as much information out of these pieces of contributed information as we can. One of the things we do is we take an expert. So for example, we could take Phil here, and we could ask him to do some work on the website as well. And because he's an expert, a trusted person on the site, we promote his classifications higher than anybody else's. Now, Phil will have overlapped with somebody else on the site. Because we show multiple objects to multiple people, Phil will have classified this galaxy. A random user on the site would have classified the same galaxy, and by comparing their classifications, their opinions, we can actually change how much we trust that user. So we actually update how we score that user and weight that user. That user will have overlapped with another user, and we take that user score and piggyback that onto that user as well. And we do that throughout the entire system. So the main mode that we've used to boil down people's opinions into science has been this kind of weighting score, like this kind of iterative scoring and weighting of users throughout the system. And that works quite well, but it's not great. And what we're trying to do now is move towards a better model that's going to help us out more. We had a project looking for supernova a few years ago, and we were showing people these triplets of subtracted data, so the new reference image and the difference, and looking for transients, which is going to be important for LSST, obviously, looking for supernova explosions. We eventually shut that project down because the machine learning algorithms that could do this got as good as the system that we produced, and that's important because for us, it's about not wasting people's time. So if anybody comes to us on one of our projects and says, I've got a computer learning algorithm that can do as good a job as a crowd full of people, we shut that project down because we don't want to be wasting people's time. We want to work with machine learning and work with areas that need our help. But with this project, we could do something kind of interesting. Because we did follow up on the supernova, we created a database of kind of truth of the results, like the actual answer at the end of the day. And what that let us do is it let us create a model for each one of our users. We could look at what it turned out to be a supernova. We could look at what they'd said it was, whether they said it was a supernova or not. And we could begin to model what their response was to real supernova and what the response was to not real supernova. And so we can create confusion matrices like these. So this user here, for example, whenever it's not a supernova, he says it's not a supernova. And whenever it is a supernova, more or less he says that it is a supernova. And so he's a high-value user. He will tell us whether he's a good discriminator of supernova or not supernova in these images. Somebody like this is always pessimistic. They will always tell you that it's not a supernova, even when it is one. And so we don't have any discriminatory power there. And similarly, we can classify people into these different modes. The interesting thing is that if you do that, you can actually get more information out of the classifications the opinions users are telling you than is actually just contained in whether they're right or not. To give you a really sort of like extreme example, if you have a user who you've modeled to always tell you that there's not a supernova there when there is a supernova there, and that there is a supernova there when there isn't one there, so they get it wrong, but consistently wrong, that user's classifications are actually as valuable as somebody who gets it right all the time, because you can just invert their opinion and actually get value out of it. And that's the extreme case. But if you model people and you know that they're probabilistically going to tell you the right answer this many amount of time, when you come to incorporate that user's classifications, their opinion, you can actually derive value from them even if they're wrong. And so by using this kind of model, this kind of modeling of individuals, we can eke out a huge amount of information in our system and make it more efficient. Yeah. So to give you an example of how much better it is, this is the supernova project. This is for just taking a weighted sum of users. This is of our standard methods. This is taking the mean, which is even worse. And this is using this kind of probabilistic modeling of the users. We get a much better true positive rate and a much lower false positive rate by combining their opinions in a different way with this modeling. And that's very, very cool. The other thing it lets us do is that we can actually monitor their model over time. We can monitor their proficiencies over time. So this is a plot showing how good a user is at distinguishing between not a supernova and a supernova. The closer this green line is to the top vertex here, the better they are. And you can see here they start off their journey through our project and they get better and better and better steadily. Then they kind of plateau for a long time. And then something happens here, and we don't know what it is, but they become really bad at distinguishing. They actually become a non-contributing user to the project because we don't have any distinguishing value in their classifications anymore. We have no idea what happened here. We don't know whether their confidence was shaken because they saw something that they didn't understand. We don't know whether the telescope was producing data which looked differently that night, and so it changed their ability to classify it. We don't know whether they just came back from the pub and had a few drinks, and so were a little bit worse off than normal. But if we can detect this kind of drop in real time from users, then we can actually intervene and we can give them something easier to do, and we can make sure we get them back to being a good contributor to the site. And so this kind of modeling of users is really important, and doing it in real time, which is the component that we're working on just now, and actually one of the reasons I'm here with Phil, it can be hugely valuable and hugely important. You can go even further than that, though. If you've modeled your users well enough and you're beginning to model your data in real time as well, you can ask the question, well, what user is going to give me the most discriminating opinion based on their previous contributions to the project? And so this is a paper from Tammy Waterhouse at Google. It's called Pay by the Bet, Information Theoretic Metric for Collective Human Judgment. And what they're looking at is using information theory to say who in this pool of people, given their proficiencies, will give me the most amount of information for this thing at its current state, at its current time. And so you can actually schedule people on pieces of data a lot better than just by doing it randomly, which is what we do now. You can see here that the score, it starts off quite low. It starts off worse than just random methods, and that's because it's learning. But gradually as it learns, it becomes a far more efficient process. So really what we're doing is we're saying we've got classifiers out there, we're showing them data, we're modeling the proficiencies of those classifiers, and then we're assigning data to them where they're most suited and most able to cope with that. And so that brings us to kind of the model of the universe that I want to kind of produce for the next 5-10 years. It's a little bit more complicated, but it's worth it. Because we can do classifiers, and we're not talking about just people anymore, we can actually use machine learning algorithms in that loop as well. So imagine you've got a human asking for data and classifying it, but at the same time you've got 4 or 5 machine learning algorithms, completely different machine learning algorithms, asking for data as well, consuming it, producing an answer, and it's sending it back to us. Our system would monitor each one of these classifiers, regardless of whether they're human or machine learning, and like map out their proficiencies. And that means that we actually send data to the machine learning algorithms that we know they can cope with and they know they can give us a good answer for. And we take the rest of it and we give it to the human crowd to process. So as the LSST dumps data in nightly to our system, the idea is to parcel it out to whoever's best able to analyze it. We get information back, we make decisions, we can send information off to do follow-ups or whatever. And the nice thing about this is that over time, what we can do is we can take the human classifications where they're better than machine learning algorithms. We can feed that back around the system and use it to retrain the machine learning algorithms. And so hopefully over time, what we hope will happen is that you would gradually edge out the people in this process and get an actual automated methods that gets as good as them and over time. And so I think that's really exciting. I think that's something we can build. We've got the technology to do it, and I think we're going to try and put that in place over the next 5 or 6 years. So if you think there's a use case for this and with your data and your problems, come and talk to us, and we can try and figure out a solution to it. The other part of what we're doing is something slightly unexpected. It's something we didn't expect to happen, but it's worth talking about, and I think it's important to realize. And that's, we've been talking about crowdsourcing data analysis, but I think you can actually crowdsource hypothesis testing as well and actually get people out there to help you understand your data and do quick runs. In the same way that we hand off thoughts to master students and early PhD students to go away and have a play with and give us a brief answer about whether it's an interesting problem to then go and do some more work on. I think the crowd is actually good enough to be able to give them a suggestion of some analysis and to let them go away and work on it and tell you something interesting about that analysis. This is a lot more controversial, I know. It's like, can we treat members of the public just like master students? And I think the thing to realize is that a lot of the people who use the site, they're not just, like my mum, or they're not just like, my mum was a very smart, intelligent person, but they're people who have they've gone through training in terms of another field. They might be computer scientists, they might be people working in the city doing quant analysis stuff, they've got a lot of skills there that are not necessarily, they're not just necessarily people you would meet on the street. There's quite a skilled set of people in there. And what happened is that we started to see that happening organically within our projects. When we launched Galaxy Zoo, we had a forum set up alongside the project, and we thought people would just hang out there and chat, and we thought it'd be a good way of retaining people in the project if they felt about a community. But what started to happen was things like this. Some of the users started noticing these green compact objects and the images we were showing them. And on the forum, they started making a bit of a joke about them. So this is the first post. The post on the forum is called "Give Peas a Chance," which is a fantastic pun. And they were putting these little objects they call green peas in this forum thread. And you can see it sort of starts off as a joke. It starts off as kind of like, these galaxies look like peas. Let's put them in a thread called green peas and have a look at it. But as we went further and further through that thread, people started posting not just images of these galaxies, they started posting spectra. And we never expected this. People were going off to the Sky server, they were putting in the idea of the galaxy, they were downloading the spectra, and they were sharing it with other people in the forum. This started happening regularly. They started collecting spectra. They noticed that they all had this very large O3 spike, and they started to say, this is interesting. This is a class of something. This is something which looks as if it's actually distinct from other things. They started to do things like signal to noise. Our forum recreated signal to noise in terms of stacking all these like spectra on top of each other to see whether the feature went away. They did some fairly sophisticated analysis without very much interaction with a science team or a science member. So this was completely community-led. They even got to the point of producing a fairly strict and well thought out definition of what these objects were and what could be considered one of these objects or not. And it turns out that these objects they were looking at are a class of galaxy that the SDSS pipeline was like inappropriately assigning to be stars because they were so compact in the sort of model that was there. And so what they were doing was they were providing oversight for an automated method. There was an automated method that was not classifying something correctly, and the users came in and they spotted this, and through their own efforts and their own research were able to tell us there's something interesting here, we think it's something you should look at, and that let us fix the algorithms. Of course, once you know what these things are, you can write like very simple selection rules to pick them out. They're all here, but I think it would have been years, if not, never, that these things were picked up on if it hadn't been for people looking at the data. Like having human eyes in the data, having the concept that you can go in there and see something and flag it up because it looks weird is actually a really powerful, a really sort of important process in this. Something similar happened with our Planet Hunters project. Planet Hunters is taking Kepler data, publicly available Kepler data, and putting it on an interface like this, which asks people if the star has any transit features, and allows them to mark out a box of transit features. We thought this project was going to be a massive flop because you're basically asking people to look at boring like graphs of data. It turns out to be one of our most popular projects. We've had something like 15 million classifications in this project alone. That's 15 million chunks of Kepler light curve looked at and analyzed. Similarly, what happened was we saw people starting to do things in our forum software that was interesting. This is kind of a plot of activity on the website. So blue here is analyzing a piece of data in the interface, and green here is making a comment on our forums. And this is kind of a typical user. This is actually me. I'm quite lazy, so I don't talk to people all that often. So you can see here that this kind of a mix of stuff. One of our users, Kaijin, is completely different. He started off classifying on the site a lot. He got more and more involved in the forum, and then now he exclusively hangs out in the forum and does stuff in the forum. Now, naively, you might think he's not contributing to the project anymore, but when you look at his posts, he's doing things like this. He wrote his own folding algorithm to take the light curves and do folding to sort of amplify the signal from the transients. He started going off and finding the images of the stars that he was looking at to sort of figure out whether there was eclipsing binary pairs in the background that were causing issues with the data. And he eventually, was even doing things like looking for cosmic ray detection within the data that was there. We were so impressed by what he was doing that we bought him a copy of IDL because he was like struggling with it to do all this data processing in Excel, and so we were like, here, have a copy of IDL to do some more with this. And Kaijin has kind of marshaled the community. He's teaching the rest of the community how to do this kind of analysis, and there's a number of people on the forums now who are going through this is what a grad student would do, right? This is what an early master student would do, and he's helping the rest of the community learn how to do that. And so the question we can ask is, let's say that, I was talking to David the other night, and he was saying he's got this massive list of like half-thought ideas and sort of, little things that he wants to do, but he doesn't have the time to do them. What if we could put those out to the community and just say, I think it would be really interesting to see if Kepler planets correlate with your zodiac sign or something, I don't know, whatever, and allow users to go away and actually look through that data and give you a first pass of whether that's an interesting idea or not. What do we need to make that happen is tools. And so the problem that Kaijin had and the problem that most of the people in our forums have is that the barrier to entry of this kind of data analysis is getting the tools set up, getting your environment set up and learning how to use those tools. We all forget how much IDL was a complete mystery to us when we first opened it up, or Python is a complete mystery to us when we first opened it up. And I think there's something happening just now which is actually really important and can help with that. So there's this quote I found on a website, a blog that I read very often. It's actually from a web developer. And it says, something happened a few years ago in web browser land. Did you notice it? I didn't, at least not right away. At some point recently, the browser transformed from being an awesome interactive document viewer into being the world's most advanced, widely distributed application runtime. And I think that's definitely true. We think about our web browsers as a way of looking on the internet, but increasingly web browsers are becoming application runtime spaces. And so what we are interested in doing is taking that runtime space and producing tools that will allow people to analyze data in a very simple, very meaningful way. And I want to very, very quickly do a live demo of that, which I'm probably going to regret instantly, and just show you kind of the type of workflow that we go through. So we've a number of tools that kind of are aimed at allowing users to make these discoveries and make deeper ask deeper research questions with our data. This is what we call Talk. This is our custom-built forum software. And it's a forum software that's all kind of focused around commenting on objects. So this is actually Space Warps. This is a project looking for gravitational lenses. And these are images from the CHFT of the space that's in there. And so people can come on here. They can come on and they can add comments to this object just to sort of flag it up with things. They can add hashtags, which then become searchable. So if you want to see every other object that's tagged with that hashtag, which apparently there's none, which is disappointing, we can do that. So let's go back and see if there's a popular one. So if we want to look at for any object that's been tagged with red arc, we can do that, and then we see all the objects that are in there. People can make collections of objects as well. So if we come back here, we can find hopefully a collection. Is Elizabeth Tita's collection? Yep, so she's got a collection here. And so she's got a collection of simulations, which is what we put in to measure users' proficiency. And she can collect those objects together, and then she can make comments about those collections and share them around. So the idea here is that for the green peas project, you could collect all those images of green peas into a collection and then do some more analysis with it. But once you've made those collections, what do you do with them? Well, we're starting to play around with this idea of what we call tools to the universe. And so we can create a dashboard, so like My Galaxies. And what we can do here is we can bring in data from that system. So let me say if I want to bring in either data from the Zooniverse or the Sky server directly, I can go to my recents. I'm going to bring in 12 recents. And that brings in some galaxy data into this system. And then what I want to do, I want to export that data. So I've got a bunch of tools that can help. I want to, first of all, see what these galaxies look like. So I can bring them into the subject viewer. Basically what I'm doing is I'm taking this data container and I'm tying it to this tool here so I can look at these galaxies. I can look at their statistics. I can look at the images from them. I might say, actually, I want to know where these are in the sky. So we can bring in, again, the data into a plotter in the sky and see that these are where the galaxies are located and begin to see some of the strips of data. We can start doing statistics on some of the data. We say, I want to know what the statistics are for the IRA and DEC, and we get mean, min, what of that. And we're beginning to build more sophisticated tools as well. So this is one of my favorite. We just built this recently at a hack day. This is the whole color magnitude space for Galaxy Zoo. But what we can do is we can bring in that data. I can plot where my galaxies are in that color magnitude diagram. I can even mouse over and see what typical galaxies are in that region, if this is going to work. Yeah, so in that bin there, this is the kind of galaxies that are there. And so we can mouse around that and get a feel for how typical or how atypical our galaxies are. And this is just the beginning. These are just the tools that we're playing around with just now. But if we can create a suite of these things online, we can allow people to do deeper analysis and deeper engagement with the data. The nice thing about all of this is as well, if I copy and paste this URL to somebody else, they can come on and look at my dashboard. They can also copy my dashboard and then start making modifications to it and start their own analysis based off of what I've done. And so there's a kind of a nice way of allowing people to get involved in scientific research without having to go through the sort of overhead of setting things up. Just to give you an idea of the kinds of things we can do in the browser, this is a fun tool we've been prototyping recently, used for the Kepler light curve data. This is a Kepler light curve with a planet in it. But really what we wanted to do was allow people to do that folding task dynamically, so we can fiddle around with the smoothing window. So we can try and get this nice and smooth. There we go. And this is all happening in the browser. And then what we can do is we can change the period of that. And there we go. We see the transits much more clearly, and we can see that the period is there. And so building these kind of tools to plug into existing data sets and allowing people to use them to explore and then communicate their results is really important. The way we communicate the results is through a process like this. This is Letters. This is a website we've built to basically allow users to take what they're doing and write them up in kind of a faux kind of like journal type way. And the whole idea with Letters is that it should be like the old system of publishing where it was actually just an idea you were sharing around with people, and this is a way for them to communicate it. So you can see here people are using this system to write short paper-like documents with an abstract, an introduction. They're bringing in data, bringing in images, and this is communicating their ideas to the rest of the community. And so we can try and take people through this full arc of discovery. And that's actually what we're trying to do with the project just now, called quench.galaxyzoo.org. I won't talk too much about the science of this, but this project here is trying to get people to classify about 6,000 galaxies, take the data into that tool system, analyze it with greater detail, and then actually what we want them to do is collaboratively write the scientific paper that's going to propose the results at the end of it. So that's kind of where we are. This is all still experimental. We're still learning how to do this with people, but I think it's really exciting, and it can be a way of really sort of pushing the boat out on what we're doing with citizen scientists online. So really, I just want to leave you with these two thoughts. In the age of LSST, I think these social computing systems can really complement machine learning, can create a structure where we get the most amount of value out of machine learning and individuals' attention. And I think that if we really think about it and really work hard, then we can enable an entire community of people who are smart, who understand things like data, and we can teach them about data to be a kind of army of master students or grad students to go out there and help us understand this data as we go along. It's not going to be easy. We're still trying to figure out a lot of it, but I think it's worth pursuing, especially in this kind of age of big data. And that's where I'll leave things.
That was a great talk. So people are not deterministic in the things that they say, even if you show them the same image. And obviously an expert looking at a galaxy might call it an SC one day and then another day an SB.
Yep.
How much are you sort of doing null experiments with individuals, and are you allowed to, from sort of a human subject's perspective, to get a sense of essentially error bars on people?
Right. So there's a couple of different ways we can do that. We're getting better at it. With most of our new projects, we try to inject simulated data, so data that we know that there's a definitive answer for. With those projects, what we can do is we can actually dynamically change the rate at which people see that. So it never goes away completely, but at the start, they see a lot more of it so that we can bootstrap our models of the individuals, and then gradually it will fade away. But there's maybe some sort of value and then introducing it later on if we see a dip going in their proficiencies again. In terms of how much experimentation can we do in people, as long as we don't want to publish, I think we can do as much as we like. If we want to publish those data, and we're working with Syracuse University, their psychology department there, to run a number of tests on there to try and work out why people do what they do, why people have different reactions to different things. So for example, there's a paper we're looking at just now, which has been looking at the effect of micro breaks on these crowdsourcing tasks. So if you've got a highly cognitively intensive task and you force people to take a short break, even just like a switching of what they're doing for a couple of minutes, it seems to make them stay around for longer. And so those kind of experiments we can run and publish through this partnership we have with other places that are interested in this stuff. To me, I think I think you're right. I think we have to treat this like a system and really treat it like something to be optimized and something to get the most value out of, because that suits our users as well. They want to contribute as much as they can, and we don't want to waste their time on something that's not valuable. So if we're not correctly measuring those error bars and we're not correctly modeling our users, then we're doing them a disservice too. So I think we're starting to do that now. We're getting better at it, and I think that's that's the next challenge that we're facing for the next 5 or 6 years.
Yeah, I mean, that was great on many fronts, I think, the whole activity. But I was just curious if you have attracted the attention of academic social scientists, or are they largely disjoined from this activity?
Some of them are, some of them aren't. We've got some really good, as I was saying, the guys we work with in Syracuse are social scientists, psychologists, and they're really interested in trying to get as much information out of the system as possible. What we've found is that a lot of social scientists who are interested in this area are going about it in a slightly weird way. They're building their own projects that are just being used to analyze the users. And those are kind of weird, fake systems that don't really capture the characteristics of a live system like ours. So one of the things that we're doing just now is working with them to give them access to the data that we have to understand how these social systems work. We're going to try and make all the data we have available, what we've collected over the past 4 or 5 years, available as an open data set to allow social scientists to come in and study this stuff. So I think there's definitely a community of people who get it there, and there's a community of people who are still trying to figure it out, but we're definitely working with them. The grant that I'm currently funded on is NSF grant, Social Computing Systems, which is a mix of computer scientists, social scientists, and scientists who are analyzing data. So it's definitely a new field, and it's definitely one that's growing.
So I have a question.
Hey.
I'm holding the mic. As more and more browser usage goes to mobile, how does this, do you have a decreasing pool of users with spare time sitting at their
I think that's a really good question. So mobile is becoming more and more prevalent. I think if we can tap into that, that's actually a really good place to be. So mobile has its own challenges, which are you might not have a connection. You might have intermittent connections. We're beginning to solve some of those problems. The biggest problem that we have with mobile is that the screens are so small and your finger is such an inaccurate pointing device that for a lot of our projects, it's kind of hard to imagine how you're going to get good data out of an interaction with a phone. But in saying that, we're open to trying projects that will purely run on the phone just to see how that works and experiment with that. In terms of whether we're losing people's time to mobile devices, I don't think so. I think people make a conscious effort to sit down and do this. And so I think it's a different use case. It's not just about idly browsing. It's like saying, I'm going to go classify some galaxies now. And so I think that people who we have there who are dedicated to our projects aren't doing a trade-off quite the same way. And the same way, I guess, is like you wouldn't play, I don't know, like an Xbox game on your mobile phone, or maybe you would. You know, there are other things you would do on a computer, and you still do on a computer because it's the best place to do them.
So to kind of follow up on that, and then back to your question about data packaging, how much interaction have you had with developers in that community in game design? Because it seems like, I mean, at least from a naive perspective, there's nothing that keeps this from being the next Angry Birds.
Right, exactly, yeah. So our team is basically made up of developers. So even the scientists who are working on a team are developers and have become developers. So like we started out being a couple of astrophysicists who taught themselves Ruby on Rails and JavaScript, and we've begun to hire more and more developers. Part of the issue with that is we can't pay them as much money as Google can, so it's kind of hard to get good people, which I think is probably something that the LSST guys, when you're talking about the cost being in humans and people, it's actually quite hard to hire good people because there's so many other people who will give them way more money to do something else that's probably as interesting. That's an aside, sorry. We talked to them. We're presenting a paper at a gamification conference in Waterloo. We're a little bit worried about treating these like games, as we saw like the motivation that people have for doing the projects is they're contributing to real science. And some of even when we've introduced very simple game mechanics like scoring mechanisms or ranking systems on the websites, it's really been popular with some users, but there's a whole other raft of users who get really turned off by the gamification of our sites. And so we think there's something pure and something powerful in saying you're actually contributing to science and this is how you're doing it. And we're nervous a little bit about going too far in the kind of game design direction with our projects. Other people are doing things which are far more gamey. We'll see how it pans out. And we're open to trying new ideas, but we think there's risks there and not just benefits, and we want to be careful of that.
So first of all, I want to say I think this is just really interesting and something that can really be even more prevalent, like pervasive in science in the future. And the first place that I actually heard about this was on YouTube from just like a random YouTube video. And I was just wondering what you think about getting the word out about this type of thing. Does it come up on like stumbleupon.com or those other things that college kids use to waste time?
Right.
Stuff like that?
I'm not sure about stumbleupon.com. Today we haven't really made a big push in terms of recruiting people. We know we've just gotten by in terms of the publicity we get off of news stories when we launch a project. We're still, for the first couple of years, we were able to like sell our story on the sense that people are doing real science online, but that's become quite boring now to journalists. So it's more about kind of the uniqueness of the project that sells it. We haven't done a huge like marketing push. We don't spend any money on advertising or marketing. That's maybe something that will change in the future. But it's mostly by word of mouth and mostly by kind of getting out there. So we might be able to attract a huge, larger community if we do that. There's arguments about their motivation then, and sort of like, do we want to just get people on the site doing stuff because they heard about it or not? I'm not sure. There's issues with that as well. I think that we might need to think about that in future, but one of the ways that we've been expanding our user base is just simply moving into new areas. So like we're working with biology, we're working with climatology, history, and so that brings on people who have an interest in that area, who start doing stuff and then discover some of our other projects and contribute to them as well. So there's kind of more about expanding into different areas, I think, than the marketing, but that's something we can look at for the future as well. Yeah.
Yeah, one thing I guess I didn't hear enough about was how the results of the projects get back to the scientists, and when you've decided how many people, when you decided how that you've seen enough people classify certain things that
Right.
that this is a good classification, and
Yeah.
how is the data collected and on what timescales?
Right. So So I think there's 3 questions in there. So like in terms of how we work out how many people should see something, as I was saying before, up to now it's been very much just like a hard cutoff. We do a beta test, we get some data from that, so we analyze a small section of the data, we see the results, see whether they're good enough to make a statement about science. And all these sites are designed to answer very specific questions. Whenever we build a site, we have an initial paper in mind that we're trying to answer. So we've got quite good ideas, roughly what the data load is going to need to be to consider something done. We're trying to move to a future model where we actually dynamically determine that through these kind of modeling concepts, like actually having a model for how confident we are an object is of one class or another based upon how proficient the users who have classified that are. And so that may mean that one object gets seen by one user who is always right, and so we can just say that's done now. And then like other objects are seen by people who are less good, and they take maybe 20 or 30 looks to retire that object. And so there's different strategies we can use to do that. In terms of how it gets back to the science team, each of the projects has a science team involved with it. So whenever we start a new project, we recruit, or it's usually suggested by that team, the site to build. And so we work with them continuously throughout the project to do data analysis, to help us design the experiment, design the website itself. And so they're working with us right from the get-go. So it's not just like we're taking the data and then giving it off to a scientist. And I can't remember what the other question was. Oh, timescales. Like, yeah, some of our projects get finished in like a week. The Snapshot Serengeti project, we burned through about 500,000 images of the Serengeti in less than a week because it was just insanely popular. Other projects are slower and take a lot more time, so it varies from different topic to topic.
So I'd be happy to tell you more about the SpaceWorks experience over coffee.
Yeah.
Robert, if your question is short, we'll have a short answer from...
Well, it is a question. So the analogues of colloquia, seminars, and conferences, that's all real scientists use for intensive learning episodes.
Right.
Is there some analog to those coming beyond the 4?
Yeah, I think that's a really nice idea. We've been experimenting with Google Hangouts recently, so we've been experimenting with having the science team have a Google Hangout and talk about aspects of the project and sort of really push ideas and do teaching and sort of, differ back and forth with the community. Right now, a lot of that kind of learning happens in the forums just from peer learning and scientists being in the forums as well. But yeah, I'd love to experiment with that kind of thing. So like using the kind of the massive online course approach to maybe tackle individual parts of the sort of the concepts that need to be looked at for a project would be definitely something we'd like to try. But that's a little bit down the line as well.
Okay, I'm supposed to rule with an iron fist, but I'll let you have the last question before we go for coffee.
Okay, so I'll try to be kind. So novelty and outreach aside, which are obviously off scale, if we want to put the result of what's been done in sort of stark terms and, research per dollar spent,
Right.
Or research per, human time spent, how do you think that stacks up against, what a typical research group might be able to do if given the same amount of money, with the same amount of time?
Mm-hmm.
So I was just 55 papers doesn't seem very striking to me as an output if research is the main goal.
Sure. I think part of that is that we were, so part of the reason we've done 55, which I think is actually not too bad given the sort of, the core team has been for most of the life of the universe 3 or 4 people. So in terms of investment and money into the core team, it's 3 or 4 salaries for the past umpteen years. In terms of human attention on the websites, we run at about 130 people hours every hour on the websites of human attention. I think that we were learning for a long time. We've started with a couple of projects, very small projects, and we're opening them up, and we're getting better at building them faster. So I think the rate of publication is going to increase with that. We've been learning about how to work with science teams to properly do this. And the other thing to mention is like all this data is eventually going to become open source so that anybody can go in and use this data. We've just put the Galaxy Zoo morphology classifications into the Sky server. I think it's a hard thing to measure. I think it's something we should definitely be doing more and looking at more. But I think it's also slightly conflated by the fact that I think some of the problems that we're trying to solve, I'm not sure you could solve them by other means. I'm not sure like if you paid 3 salaries to a group of learning people to try and solve the project, that there's any guarantee that within 3 years they would have come up with something that does as good as the crowd does. And so I think that there's problems that can only really be kind of tackled with this approach, and I think that it's worth tackling a lot of those problems. So I think it's hard to say, and I think the value is something that we need to measure, and it's something that's important to us because our mantra is that it's all about the research. And so yeah, we should probably have some better numbers than that, but I think it's actually pretty good. I think it's not too bad.